For this video, we are to evaluate the given function along the interval from 0.00 to 2,4 along a straight line between them. This is in connection with the real line integral, but using the specific parameterization for the path, which is a straight line. Let's not forget that our real line integral expressed as p of xy dy plus q of xy dy along your path C is equal to this expression here. We'll have the integral of your p of x of t y of t times the first derivative of your x of t. You will have here, sorry, this is not dy, by the way, I forgot. This is actually dx. You have here plus q of your x of t y of t, then the derivative of your y of t with respect to t from a to b. Okay, this is how the expression would look at. Of course, given by the expression, your p of xy corresponds to the function with dx. You will have here 2y plus x squared, and then your q of xy corresponds to the function with dy, so that's actually equal to 3x minus y. Okay, so this is very important because later on, as we parameterize our x and y in terms of t, variable t, we are going to substitute that here. In short, for this entire equation here, we need both x and y, unlike the previous videos. At the same time, for q as well. So first, let's try to look at the parametric form for x of t, right? We already know this one here. I already covered this in one of our videos. Our x of t for real line integral is just equivalent to x sub 1 plus t times the difference of your x sub 2 and x sub 1. Our x sub 1 is, of course, the x value of your first point, the starting point, and your x sub 2 is this one here. So basically, it's just 0 plus t times your x sub 2 is 2 minus 0, which would give us this expression for x of t, which is 2t. For our y of t, this is also equal to y sub 1 plus t times the difference of y sub 2 and y sub 1, which would give us, again, this is our y sub 1, this is our y sub 2. This is 0 plus t times 4 minus 0, which would give us the expression you will have for t. Take note, this parametric form is specific to the path, which is a straight line. If it's not a straight line, we'll have separate videos for that. We're going to use another parametric form for x of t and y of t. Okay? But of course, this is not automatically what we need to substitute there, because our given function is actually 2y plus x squared for p and 3x minus y for our q. We will have the corresponding illustration later on, because we need to identify as well these components, the first derivatives, to complete our process. Now, our x of t is 2t. So our x prime of t is derivative of this with respect to t. That's actually 2. For our y prime of t, which is derivative of this with respect to t, is equal to 4. So this is good. That is good. This is yet to be identified. We'll have that the next one here. This is also yet to be identified. That's also the next item we're going to show here. The next item that we don't know is your a and b. Take note that when we discuss the real line integral, its parameterization together with the complex line integral, we were able to understand that for our t is between a and b, the most convenient value for a and b is actually 0 to 1. You can actually use other values for a and b. You can even 0 to 5, 0 to 10, it depends on you. But the most convenient and the easiest way to use is 0 and 1. Hence, our a is 0 and our b is 1. Now, there is also another method to answer this one. They use the idea of connecting these points and getting the equation of a line. And we might have different forms for x of t, y of t together with the first derivatives. But to be consistent with what we did previously, in one of the examples for a path containing straight line and for the complex line integral, let's continue doing this. Okay, before we use this entire expression, as mentioned, we need to identify your p of x of t and then y of t. Okay, together with the q as well. Take note our p. Let me move this down here so that I could illustrate it better for us. Take note that our p of xy identified earlier in our given is 2y plus x squared. That would mean if we're going to change it to our parametric forms for x and t, this is equivalent to 2 of y of t plus the square of x of t as we substitute x's and y's. But since we know that our y of t is 4t here, so you have 2 times 4t plus you will have here your square of your x of t, which is 2t. Okay, so that is actually our form for our function, which could be simplified further as 8t plus 4t squared. This is for the first function. Take note of that. For our q of x of t and y of t, let me move this down again. We know that our q, sorry for that, our q of x and y identified or given is 3x minus y. So 3x minus y. Now substitute x of t for x and y of t for y. This is 3 of x of t minus y of t. Again, our x of t is 2t. That's actually 3 times 2t minus your y of t, which is 4t. Simplifying that, 6t minus 4t, this is equivalent to 2t. That is the equivalent form of this expression. Now, all of the things we need are already identified, starting from the boundaries of a and b, your functions using the parametric forms, and the first derivatives already identified here. Let's now complete this at the bottom. That's actually equivalent to, okay, from a to b. Okay, so a is 0 to 1. Let's start first with the function parametric form for our p, which is actually this one here. That's 8t plus 4t squared times the first derivative of your x of t, which is 2, times 2, plus, take note, these are all under one expression. The next would be for your q using the parametric form. That's actually this one here, 2t times the derivative of your y sub t, which is y of t rather, this one here, which is given as 4. These are all with respect to d of t as indicated in the formula. Now, as you can see, we now have expression in terms of t, no longer having x's or y's. Let's continue that. You will have here, hopefully the space are enough, the integral of, you will have here, as we multiply 2, you have 16t plus 8t squared plus 8t dt. We can combine the t's. You will have 0 to 1, 8t squared, 16t plus 8t is 24t dt. By linearity property, you have 8 integral from 0 to 1 of your t squared dt plus 24 integral from 0 to 1 of your dt. Okay? Let me see if this space is enough. For your first 8, as we take the integral of t squared dt is actually t cubed over 3 dt. We know that. And the integral of your t dt is t squared over 2. Let me remove this dt here. That would mean for your first, this one here, you will have the expression times t cubed over 3 from 0 to 1 plus 24, and this one here, you have t squared over 2. Again, my space is not enough. Let me rewrite this entirely. So we have here 8 times t cubed over 3 from 0 to 1 plus 24 t squared over 2 from 0 to 1. Okay? So simplifying that by substituting the upper boundary for each of the terms minus the lower boundary, you have 8 times 1 cubed over 3 minus 8 times 0 cubed over 3 plus 24 times 1 squared over 2 minus 24 times 0 squared over 2. This is 0, that's 0. So you will have here 8 cubed plus 24 times 1/2 is 12. To combine them, of course, by LCD, by 3, that's 36 plus 8, you will have here 44 thirds. This is the answer to the question. This is the integral of the entire function here, okay, from 0, 0 to 2, 4 along a straight line path, okay, using the parameterization for that and all of the necessary details herein. Okay, so this is how we solve that, especially if our given P and Q functions are combinations now of x and y, not similar to the previous one where we only have one variable for each function. Thank you very much for watching.